Here's problem number 27 from section 4.1. We're asked to find the extreme values of this function, and there's no restriction in terms of it being on a closed interval. Let's start by investigating this function by looking at its derivative. When I take the derivative, I get dy dx is equal to 1 over 2 times the square root of 3 plus 2x minus x squared, and then multiply that by the chain rule, and we end up getting 2 minus 2x. If we do a little cleanup there, we can factor a 2 out of those two, and that factors there, leaving us 1 minus x on top and the square root of 3 plus 2x minus x squared on the bottom. A couple of things also here. We may, well, there's no given restriction on our interval. This function may not be defined for all x. Let's just do a quick investigation. When is 3 plus 2x minus x squared greater than or equal to 0, so it satisfies the square root sign? I'm going to rewrite this as pulling everything over the other side. 0 is greater than x squared minus 2x minus 3, or x squared, or greater than 0. Sorry, the expression x minus 3 x plus 1 has to be less than 0, which means I got to get two negative signs out of here. This happens when x is certainly equal to 3. Let's just do it this way. When x is 3 and when x is negative 1, we have zeros out of this expression. When both of these things are positive, we get a positive value, which is not less than 0. When we're inside here, the negative, this part gives me a negative value, and this part gives me a positive value, which nets out to a negative, and we're satisfying this inequality. When we get beyond negative 1, lower than negative 1, we have a double negative and don't satisfy. So it's in this interval from negative 3 or negative 1 to 3 that we satisfy, and this function is defined. So let's just put that down as the domain is the closed interval from negative 1 to 3. We'll also note that those values of negative 1 and 3 make the denominator of the derivative equal to 0, so the derivative is undefined on each of those endpoints. The other place for the derivative is of interest as we look for critical values is when x is equal to 1, because that makes the numerator equal to 0. So let's investigate then this function when f is negative 1, when f is positive 1, coming from that critical value, and when f is 3. When f is negative 1, we get the square root of 3 minus 2 times negative 1 minus negative 1 squared. That is the square root of 3 plus 2 minus 1. 5 minus 1 is 4. Square root of 4 is 2. When f is equal to 1, we get 3 minus 2 times 1 minus 1 squared, which is equal to the square root of 3 minus 2 minus 1, and that is equal to 0. And then when f is 3, we get 3 minus 2 times 3 minus 3 squared, which is the square root of 3 minus 6. Something's wrong here. Something's wrong here. because if that's the case, oh sorry, that's a plus sign. This is a plus sign, that's a plus sign. So this is a negative 2 here. This is 3 minus 2 minus 1, that's a 0. With that plus sign there, we get 3 plus 5. 5 minus 1, this is 1. This one is the square root of 4, which is 2. And then this one is going to be 3 plus 6 is 9 minus 9. 3 plus 6 minus 9, and that's 0. So our conclusion, here is our absolute max on that closed interval. Here is our absolute min. And by the way, there's an absolute min there as well. Right? And then these are also local mins. And of course, the location of the absolute max is also a location of a local max. And there's problem number 27.